Hello, my name is Mason Beckmeyer and I'm representing Christopher Newport University and the ADAPT Lab for Dr. Abhishek Phadke and I's extended abstract on a secured event management system for defense networks. Why are we motivated to design a SIEM specifically for defense networks? Well, with an ever-increasingly digital world, national governments and their militaries have increasingly relied on large amounts of data for their operations. They rely on specialized and compartmentalized networks to facilitate the transmission of this data from data source to data consumer. Adversaries to national governments, whether it be nation-state actors, cybercriminal organizations, or even threats from within, have continued to tailor their operations to target these networks. According to the Joint Cybersecurity Advisory Report in May 2025, Western logistics and IT companies have faced an elevated risk from Russian cyber espionage attacks since 2022. Some cyber espionage attacks in the past have targeted logging systems and data integrity. For example, in the SolarWinds supply chain attack, attackers inserted malicious code called Sunspot, and malicious teams discovered that some of the data logs needed to trace the timeline of the attack had been overwritten or were entirely missing. Our research objective is to design a blockchain-enhanced SIEM that fulfills NIST and DoD cybersecurity standards. Our parallel objectives include tamper evidence. When off-the-chain log data is tampered with, we can compare the hash of the log data off-chain to the hash stored on the chain, validating that log data has been tampered with. This ensures we have cryptographically verifiable audit trails. We aim to evaluate our system's capability for functional event messaging and to measure latency, throughput, and compliance on the private quorum network. First, we need to discuss some background information about blockchain. The technology was first introduced by Satoshi Nakamoto in the 2008 Bitcoin white paper. It established the concept of the digital ledger where transactions are cryptographically hashed and linked together in a sequential chain. While Bitcoin focused purely on decentralized currency, Ethereum later expanded the idea by adding smart contract programmability, allowing developers to create automated, trustless applications on-chain. For enterprise and systems being built for the defense industry, Quorum provides a permission variant of Ethereum better suited for these environments. Quorum also replaces Ethereum's proof-of-work mechanism with a faster and more deterministic consensus algorithm called Istanbul Byzantine Fault Tolerance, or IBFT. Quorum was originally developed by JP Morgan Chase in 2016 as an enterprise variant of Ethereum, designed specifically for high trust and regulated environments. The goal was to bring Ethereum's smart contract capabilities into permission networks where participants are known and access is controlled. Quorum supports multiple consensus mechanisms. The first is already mentioned IBFT, the second is Raft, which offers a simpler and lower security consensus option for development and testing. On the privacy and security side, Quorum uses Tessera, a transaction manager that ensures encrypted private transactions between authorized parties. In permission blockchain environments like Quorum, validators are not just anonymous participants. They are explicitly authorized nodes that have been approved to validate blocks and propose transactions. Each validator is cryptographically identified and managed by the network owner or governing enclave, such as a specific agency or command center. This structure provides a clear chain of accountability where every transaction can be traced back to a known entity, meaning there are no anonymous or unverified actors in the system. This design significantly reduces the attack surface compared with public or fully private blockchains where anyone can join and submit data. For example, within a defense context, we may have a Department Alpha that might operate a validator node responsible for block verification, while Department Beta could be an observer node, reading approved data without consensus privileges. We could have a command headquarters that could serve as the administrative proposer, orchestrating validator permissions and network governments. This possible structure enforces hierarchical trust while maintaining decentralization among approved participants, a key requirement for defense-grade network architectures. Now, in addition to validator control, Tessera plays a crucial role in securing transaction privacy within Quorum. Tessera is a middleware layer developed by Consensus that manages private transactions between designated participants. When a transaction is submitted, Tessera encrypts the payload before it's broadcast to the network. Only the intended recipient nodes, those authorized for the transaction, can decrypt and view the contents. Tessera also allows selective visibility of log entries or hashes, meaning some information such as event records can remain confidential while providing verifiable proof of integrity to the broader network. In defense networks, this level of compartmentalization is essential. It assures that classified or mission-sensitive data is shared only with the appropriate stakeholders while maintaining integrity and auditability. Within our system, log entries are first hashed using SHA-256 before being transmitted to the blockchain. Only the hash value and associated metadata such as timestamps, source identifiers, and event types are sent on-chain. This approach keeps sensitive operational data off the blockchain while still ensuring that every log event has a verifiable fingerprint. The full log contents remain off-chain, stored securely in the organized internal databases or SIEM storage. When the hash and metadata are transmitted, Tessera encrypts transaction payloads so only the authorized validator nodes can decrypt and verify it, while unauthorized nodes, even within the same blockchain network, cannot access the underlying details. This architecture ties together three key principles. The first being hashing, providing integrity, guaranteeing that no log can be altered without detection. The blockchain ensures immutability, giving each event a permanent tamper-evident record, while Tessera adds confidentiality and compartmentalization, controlling who can see what based on mission or department permissions. For related work on the first bullet, Reguero and colleagues demonstrated one of the earliest practical implementations of blockchain-based auditing in enterprise environments. Their system used smart contracts to record audit events directly onto a permissioned blockchain, ensuring that once an event is written, it cannot be modified or deleted. Because the network is permissioned, only authorized validators participate, which strengthens integrity guarantees while maintaining operational control. This work directly informs our proposed SIEM architecture. Their results showed that smart contract-anchored audit trails are viable in controlled environments. These same contexts we target in defense networks. We extend their approach by integrating a quorum-based audit layer into a full SIEM pipeline, adding FileBeat, Kafka, a Spring-based log processing service, metadata indexing, and compliance mappings aligned with NIST and DoD requirements. Where their system demonstrates immutable auditability, our system operationalizes it. Next, Baliga and colleagues conducted one of the foundational performance analyses of the Quorum blockchain platform. Their evaluations compared different consensus mechanisms, primarily Raft and IBFT, and measured throughput, latency, and block processing behavior under realistic workloads. The results showed that Quorum achieves both low latency and high throughput, largely because it removes mining and instead uses permission consensus with immediate functionality. The next study, Mazzoni and colleagues conducted a comprehensive case study on consensus Quorum to determine whether a permission blockchain can meet the demanding requirements of financial systems. Their evaluation focused on throughput, latency, transaction privacy, and smart contract execution under enterprise workloads. The results show that Quorum consistently delivers enterprise-grade performance, high throughput, predictable low latency, block finality, and strong privacy guarantees through permission membership and private transactions. Although prior work has shown how blockchain can provide immutable audit trails, high throughput, and enterprise-grade performance, there are a couple significant gaps in existing literature. First, few studies integrate blockchain-anchored logging with formal federal cybersecurity standards such as NIST SP 800-53 or the Department of Defense Risk Management Framework or DoD RMF. Most existing prototypes focus on integrity and performance solely, but they stop short of evaluating whether a blockchain-enhanced SIEM can satisfy the compliance requirements that defense networks operate under. Second, few studies evaluate the true behavior of IBFT consensus under adversarial or partially compromised conditions. Prior evaluations generally assumed well-behaved validators, and understanding how IBFT performs when nodes behave incorrectly or maliciously is an unresolved research need. These gaps directly motivate our proposed system. Our system architecture, there's a diagram on the right, processes logs through a structured end-to-end pipeline designed for integrity, performance, and auditability. First in blue at the top of the diagram, FileBeat handles log ingestion. It continuously collects log events from different endpoints and publishes them to a Kafka topic in green, ensuring reliable high-volume streaming. Next, a Spring-based processing service in red consumes these events from Kafka. This service hashes each log, stores its metadata, and handles alert generation when rules are triggered. Once processed, the log hash is anchored on the Quorum blockchain through a Solidity smart contract. This gives every log event a tamper-evident, cryptographically verifiable audit fingerprint. For storage, we use a hybrid model where on-chain we store only the hash and minimal metadata to preserve privacy and performance, while off-the-chain detailed log records and metadata are stored in PostgreSQL and Elasticsearch, enabling fast querying and full SIEM functionality. Finally, a simple React-based UI dashboard visualizes all logs, alerts, and verification results where analysts can view events in real time. To evaluate the system, we'll deploy a simulated secure environment composed of multiple virtual Quorum nodes. Each node represents a separate organizational department or enclave, mirroring the compartmentalized structure found in real defense networks. These nodes participate in the IBFT consensus protocol, giving us Byzantine fault tolerance and immediate block finality. For log generation, we will use a controlled FileBeat feed that produces realistic security events at configurable rates. Our evaluation also focuses on several key metrics: throughput, measured as logs processed per second. Next, tamper validation, where we deliberately alter logs, confirm the system detects the mismatches. And finally, we assess how the overall structure aligns with NIST and DoD cybersecurity controls, ensuring the system meets federal requirements for auditability, retention, integrity, and accountability. Our design does introduce several limitations that must be considered for real-world deployment. First, the blockchain stores only the log hashes on-chain. While this preserves privacy and improves performance, it also means that all detailed metadata must remain off-chain in PostgreSQL and Elasticsearch. As a result, full forensic information still depends on the integrity of those external systems. Third, consensus itself introduces latency. Even though IBFT is faster than proof of work, block finality still adds delays that could impact real-time analysis. Additionally, running permission validators introduces operational overhead. Key management, validator configuration, and node synchronization require maintenance efforts. Finally, while the system is designed with federal standards in mind, compliance ultimately depends on the policies of each agency and department. This architecture does contain several key advantages for securing logs in defense environments. First, this system is tamper evident. Any alteration of a stored log immediately breaks its hash chain. Second, the use of IBFT consensus gives the system resilience against partial adversarial compromise. Third, because the network is permissioned and tightly controlled, the attack surface is dramatically reduced compared to public blockchains. Only authorized validators can participate, aligning well with compartmentalized government networks. Next, the implementation is lightweight. By anchoring only the log hashes on-chain and keeping detailed metadata off-chain, we can minimize blockchain storage requirements while preserving auditability and performance. And finally, the design is compliance aligned with NIST SP 800-53 and the DoD RMF. Looking ahead, there are several opportunities to advance the system beyond the current prototype. First, we plan to introduce dynamic smart contracts that allow role-specific and department-specific logging policies. Our virtual testbed will simulate compartmentalized enclaves, but if we could deploy this in an authentic defense environment, complete with real segmentation, cross-domain guards, and operational constraints, we believe it will reveal unique performance and security behaviors. We are also exploring integration pathways with existing SIEM products like Splunk or Elastic for hybrid phase deployments. These steps collectively move the system from a high-assurance prototype toward a scalable, compliant, and fully operational blockchain-enhanced SIEM suitable for defense environments. Thank you for listening to Dr. Abhishek Phadke's and I's extended abstract on a secured event management system for defense networks.